In this video, we're going to try to understand how water heats and how it changes temperature as the heat is added to it. So what we're going to do is we're going to start off with something really cold. So we're going to say that it's like minus 40 degrees Celsius is where we're going to start. So we're going to start heating this water sample that is at minus 40. So the state of matter at minus 40 will be ice. So I'm going to have ice that is being heated up, and it keeps getting heated up until it reaches 0 degrees Celsius. At 0 degrees Celsius, water starts to change. So in this spot down here, where the temperature is changing, particles are moving faster as heated. So essentially think about those ice particles being little solid particles that are all kind of pretty rigid and they vibrate in place. As they heat, they vibrate faster and faster. So the vibrations increase in speed and the temperature goes up. So as that ice is being heated, the particle movement is faster, but they're not really moving further apart or anything like that. Now the particles are going to start to become liquid. So at 0 degrees Celsius, it takes a bunch of heat to break the particles apart. So the particles aren't moving further apart anymore. What's happening in this section is that particles move at the same speed. So they are moving at the same rate, but as you're adding that energy, they're going to get more freedom. So they're going to move further apart, but they start to move further apart. And that breaking the bonds between the different water molecules is going to allow that water to, it goes from being solid state to liquid state. And it keeps at 0 degrees Celsius until the particles become liquid. Once they've become liquid state, the particles are no longer just vibrating in place. Now they're moving freely. They kind of turn around and pass by each other. They flow. So when you were in junior high, you studied fluids, and fluids flow. And so water is a fluid. It flows. The particles move past each other, but they're all still quite close together. If you jump into a pool, the water particles will move away from each other to make space for you, but they don't, it's not like falling through a cloud of gas where there's no resistance. The particles are close together and it hurts if you hit them too hard. So in this section in here, the ice particles are becoming liquid water particles, and their particle speed stays constant, but they're moving further apart. Once we get to the stage where the ice particles have become liquid, then the particles can start to speed up again. And so in this spot, we've got liquid particles move faster as they get energy. So the heat is now changing the temperature as they get heat energy. And the particles are moving faster now. And so the temperature rises. And it's going to continue doing that until 100 degrees Celsius. At 100 degrees Celsius, water then begins to boil. And again, the energy now is going to be spent pulling those water particles further apart. And so in this section, the liquid molecules, the liquid water particles, move far apart, and the energy is being used to make them move further and further apart. This takes a bunch of energy. It takes a lot of heat to do that. But once those particles have become gases, in here you've got gas water molecules move faster. And so the temperature goes up again. And you can keep heating that liquid gas quite a bit with that added heat. So this is called the heating curve of water, and we've got sort of three really important areas. We have the areas where temperature changes because the heat is being used to make the particles move faster. But we also have some really important areas where we've got the particles are now changing the bonds between them, and all the energy is being used to change the way the particles are moving, but not how fast they're moving. So instead of just vibrating in this section, they're going to start to move further apart. In this section, they go from flowing past each other to becoming pulled apart completely. And so the heating curve of water is important because when we talk about climate, what we want to understand is that the oceans, which are liquid, take a lot of energy to change their temperature. And when water evaporates in the ocean, it's using that energy to become a gas. But those gas particles in the air can also get heated up. When we have ice in the North Pole, South Pole, glaciers, or even in the winter time, that ice takes a lot of energy to become liquid. And so when we get water changing states, there's a huge amount of energy that goes into it. So if we have glaciers that are melting, it takes a gigantic amount of energy for that ice to go from being a solid to becoming a liquid. But once that ice is in the ocean, or once that ice has become water and flows into the ocean temperature will change as the sun warms the ocean. And significantly, the ocean, because it is absolutely a massive amount of water, doesn't change temperature quickly with energy change. So when we've got the ocean temperature is increasing, that reflects a huge amount of energy change. When we have ice caps that are going away and we no longer have them, allowing to regulate the temperature, then the ocean temperatures are going to change and modify quite a bit more. What's more, gas in the air has a very low specific heat capacity, and when we study specific heat capacity, water vapor changes temperature much, much faster and with less energy than does water. So the heating curve of water is really responsible for controlling our environment across the globe and regulating the temperature of the air where the gas particles are. And the ice caps, as they melt, are really we're having there's a lot less global control of the temperature as we have less ice to control that temperature, right? So if this ice melts and becomes liquid water, the liquid water will just change temperature as it gains or loses heat. So hopefully this helps you understand the heating curve of water. You want to know when temperature would change, why when we have a state change in these sections here, why the temperature isn't changing even though heat is being added or heat is being removed, right? And so another kind of helpful thing to remember is that this is when heat is added, we went this way. But if we were to remove heat, if we were to have heat being lost, the gas particles cooling down will become liquid particles. And then those liquid particles, as they get cooled down, will start to change temperature. But then that energy is being used to make the liquid particles into ice, and then the ice can cool down again. So the heating curve kind of works in two different directions, and that this section here is going to be the melting point, or the boiling point. So that's the temperature, the boiling and condensing happens. And here, 0 degrees Celsius, this is the melting point. And the melting point is 0 degrees Celsius. At 0 degrees Celsius, the temperature of water isn't changing as the state of matter is changing.